Alrighty, folks, we left off with a run through of all of the mineral groups, and I told you there were a handful of things that we would focus on, crystallography being one of them, through just a single lens, and that being the lens of the silicates. The reason we could focus on silicates, as you've heard, oh gosh, I don't know how many times now, and probably a few more today, most commonly occurring group in the crust. The reason it's the most commonly occurring group, of course, is because its two main ingredients, silicon and oxygen, are the most commonly occurring ingredients. And so over and over again, it just goes right to, oh my gosh, there's a lot of silicates. Okay, and as you guys go through lab, once we start identifying, classifying these into their groups, you'll see that the silicates far outweigh any of the other groups. So much so, in fact, when I have you guys make the flashcards for studying for the mineral practical, the test in lab, I always suggest that you use colors, okay, colored cards. And we'll assign each group to a color. Well, we end up having to add another color, white, because there's so many silicates that they don't usually have enough cards in a collection for them, and two, we need to have 6 colors. So, but there's a lot of silicates, So we're going to talk all of today basically about what it means to be a silicate. So get ready, get excited, and silicates. So we told you just once, everything else you've heard a gajillion times, just once you've seen this SiO4. You guys quite correctly told me the other day that's 1 silicon and 4 oxygens. All right, we're going to go in a little deeper now and talk about how that's all put together. So nothing very new here. No need to hurry, scribble down all this stuff. The only thing new here is this pyramidal or tetrahedron shape. Okay, this is the crystal shape. Pyramid is not the right word. Tetrahedron is, but not everybody knows what a tetrahedron is. And in a world of gravity, where we live, if you were to set a tetrahedron on your table, it would end up orienting itself to look like a pyramid. We'll talk about that in a moment. So this SiO4, this silicate molecule, there's that molecule word going all the way back to one of our first lectures. All right, this silicate molecule contains 4 oxygens, 1 silicon, in a tetrahedral shape. Well, what does that mean? So here's that. I've been here 20 years now, and I was 4, 5, or 6 years somewhere else. Let's say 25 years now. For 25 years, I've been meaning to glue 3 racquetballs together. You'd think I could do that in 25 years. Don't have racquetballs lying around the house anymore. Perhaps that's the reason why. I don't go maybe into the sporting goods section enough. I don't know why. But this would be a great visual aid. They happen to use blue balls here. And you guys all start giggling if I say blue balls too many times. So we don't really want to say blue balls more than we need to. But I could say racquetballs. Okay? So you've got 3 racquetballs. All right? Picture them in front of your desk, since I've not managed, again, in 25 years to glue them together. Picture a little triangle of 3 racquetballs, all right? And next we need I used to call it a super ball when we were kids. They were a dime in the vending machines you going out of the grocery stores, all right? Now they're probably a quarter. They're tiny ones, though, not the big bouncy that you used to see at Old Navy for like 50 cents or whatever they were, but the tall ones, about the size of your thumbnail, super balls. Take one of those and set it in the little divot on top of those 3 racquetballs. Because they're round, there's going to be a hole in the center, right? So You set that super ball there, and then you take a fourth racquetball and you put it up on top. Well, again, we live in a world of physics. You put that racquetball on top, what's going to happen? The balls are going to roll out. So we're going to get rid of that in our head, okay? We're going to pretend that the balls actually stay there. There's that pyramid that we talked about, right? You got 3 balls on the bottom, 1 ball on top. If you put sides, facets, in the gem world, they use the word facets. You would get a pyramid with that one little super ball tucked right in the center. What do those 4 racquetballs represent in this model? The oxygens, good. And the little super ball is the silicon, good. Okay, just want to make sure we're on the same page there. We're modeling this molecule. And what you're seeing is that these oxygens are completely surrounding this silicon. It's tucked in there nice and neat, okay? And oxygen bonds, you might remember, are pretty dang good bonds. All right, so this is a pretty solid molecule. Now, as I said, it's not a pyramid. That's just what it would look like on the desk in front of you. It's actually a tetrahedron, and that's what we're trying to show you here. You see we've got 1 ball on the left, 1 ball on the right, and then 1 ball in the front, and the implication is 1 in the back. So imagine if you had like your debit card or whatever in your hands, and you could take put 2 thumbs and 2 pointer fingers on each of the corners and twist it. Would that be 90 degrees? Right? So 2 corners are opposite the other 2 corners. That's the shape. All right? That's the shape. That doesn't really, like I said, hold up in the real world. You have to be down at the molecular level, gluing these things together. But the tetrahedron is sort of that twisted, rectangular shape there. And again, we worry about this because A, crystallography, okay? Crystallinity is important. And in theory, it's not entirely self-evident, but in theory, this is responsible for how, this shape is responsible for how all of these silicates look and work. All right? So, I want to keep that in the back of your mind. Okay. So, we got it? Racquetballs, super ball. Good. Again, don't write this down as narrative. Just listen. So the silicates, most common mineral group at the surface of the Earth. There are many different types of silicates out there, each made of many different elements. And one thing they all have in common is that they're made out of silica. All right, I'll give you guys a little hint. Folks at home, these numbers apply to you for part 2 of the lab, mineral lab. Geology, folks, that is, not earth science. You guys saw roughly a dozen minerals yesterday, right? In lab. Would you say they looked fairly different? Some looked like each other, but across the board, you know, and that's why you were able to put different names on them, luckily. Every one of those was a silicate, okay? All the way up through 13 is all silicates. But do your micas look anything like your quartzes? Do your quartzes look anything like your feldspars? No, not at all. So while we have silica as this common ingredient in here, believe it or not, the simple fact that we put potassium in this one and aluminum in that one makes it look crazy different. All right? So there's a lot to be said for crystallography, for the importance of crystals, but there's also, you know, a lot of other variations. And plus, you're looking at it at the macro level. You're seriously, you know, you're eyeballing it. We're not going down into thin sections. Thin section would be like if you shaved a carrot, okay, and you get this real thin piece of carrot, you put it under a microscope. That's thin section. Believe it or not, they can do it with minerals and rocks too. Down at that level, maybe you'd see some more consistency, okay? But, geez Louise, these are as different as they can look. And moving on here, we talked earlier about the 8 most commonly occurring elements, right? it could be said then that you would expect that the remaining 6, and that's what this list is, that the remaining 6 would be the most commonly occurring things that you'd see in those formulas. Remember, you're writing down these formulas as you go through the mineral lab. And that is true. You're also going to see plenty of oxygens and hydrogens. They love their hydroxides and so on and so forth. Carbon doesn't make this list. You're going to see some of that. So there's a handful of things, and I think it's more because we're forcing you to see a spectrum in lab, okay, than necessarily a slice of the crust. If you were to take just a random slice of the crust, it might reflect this, but in lab, you see actually a little more diversity because we're forcing it. So you're never going to have to rattle off this list to me again. Remember, this is just part of that 8, and we told you all you really needed to worry about was the top 2, and which one comes first, silicon or oxygen, oxygen or silicon. You've seen this. This is just to get you back in swing. All right, so there are 4 ways that we can arrange those tetrahedra. Perhaps this is the reason why those minerals all looked so different from one another. We'll talk about each of these in turn, but isolated, chain, sheet, and framework. Isolated makes a little more sense in retrospect, so bear with us if you don't quite get what I'm saying about isolated. And pardon my crude attempts at drawing 3D. This is that tetrahedron, this is that pyramid. Feel free to draw a triangle if you yourself are attempting drawing these little structures in your notes. A triangle is more than sufficient because all we're going to be doing are connecting these triangles. All right, you don't really have to show the 4th dimension, but since, teacher. So in an isolated structure, what you have are a whole bunch of single tetrahedra that are not bonded together by any particular extra bonds. What does that mean? Well, as you're going to see in the next slides, that's what I said, more in retrospect, we're going to take one corner of this, and in case you can't make the jump from ball and stick to all ball, what is at each corner of this tetrahedron? What will be represented by each corner of this tetrahedron? Oxygens. Okay, just again, so we're all on the same page. All right, so see 4 corners, that's 4 oxygen. Your silicon's still tucked in the middle there, somewhere safe. Not really caring about the silicon right now. It's all about the oxygen bonds. So all you're going to be doing as we build up through here is connecting one or multiple of these corners to another silicon triangle, okay? So what we're saying then is in an isolated structure, they're all just jumbled together without anything really holding the triangles together. Remember olivine? Okay? You guys at home, unfortunately, you don't have an opportunity to rub olivine, but picture a piece of sandstone, if you could, or a sugar cube, if you have no clue what sandstone feels like at this point. You guys yesterday, you rubbed olivine with your thumb. Hopefully I asked you to. And what happened? You got a handful of little green crystals fell into your hand, right? And we talked about it under the guise of the hardness test was kind of false on that one. You drag the nail across it, it crumbled into your hand. You're like, oh, this is soft. I said, no. You're really supposed to test one of those little teeny tiny grains of sand, right? And see how hard that is. All you tested was, how well those grains were glued together, which isn't very well. Olivine, as you can see here, is an isolated structure. That's what it's talking about. Those tetrahedra aren't really stuck to one another very well. So you guys at home, again, if you imagine if you could rub a sugar cube or something like that, or any hunk of something granular, and it kind of starts to crumble in your hands. All right. What that tells you is that those little sugar crystals or whatever aren't glued together very well. That's what we mean by isolated structures. They're isolated in that there's just one little crystal, one little crystal, one little crystal. In contrast to, let me finally just get, some pictures for you. Olivine and garnet. All right, olivine and garnet, two examples. I forgot I added those. In contrast to, let's look at the top one, it's easier. Now you see how we're sticking those triangles together. That is an oxygen to an oxygen, and that's a great bond. Okay? That's a great bond. We call those chain structures, daisy chain. Picture that. I think hardly anybody's ever actually made a daisy chain, but everyone has hooked paper clips together, or at the very least those little paper rings that your pre-K teacher had you do around the holidays when you were a kid. All right, you staple little strips of construction paper together. That's the idea here. One oxygen to another oxygen to another oxygen. And you get one of two types here. You get a single chain and you get a double chain. Two lab examples for you are augite versus hornblende. I love this one because it's literally actually visible to the human eye. Yeah, we could get olivine to fall apart, but But remember when you were looking at your specimens yesterday, it was 9 and 10, and I always forget which one's who. But those two are hornblende and augite. One is one, you know what I'm saying? One of them is one of them. The way we talk about it in the book, I mentioned black elongated crystals for, I believe it's hornblende, right? And the augite, we tell you, looks more grainy, and oh yeah, it happens to be kind of greenish as well. Well, we're not concerned about the black versus green. What we're concerned about is the fact that you could actually see the long crystals in the hornblende. And I'd like to think that's because the chains are twice as wide. It's just that much easier to see. All right? You know, we talked about how sometimes we have to throw stuff under a microscope, this, that, and the other thing. You don't even have to do that. So next week when you get back in the lab room and you're looking at these again, even though you've probably done 9 and 10 already, go back and check that out. If my slides hold true, I probably have a picture, but I doubt it'll be as easy to pick out as if it were in front of you. You folks at home, augite, all right, hornblende, you're going to see those as well in geology in part 2. You're going to see all these crystals, okay, and all these minerals. And the numbers we're talking about, they do match up for you guys with your online mineral gallery. They only have, for you guys as reference, they have a kit. We used to get a giant thing. It got way too expensive. They have 4 minerals, 4 igneous rocks, 4 sedimentary, and 4 metamorphic. That's all I could afford, you guys could afford to get in your hands. So they have to supplement with pictures on this gallery. And I took pretty decent pictures, if I'm not bragging, but still it's pictures, you know. So imagine doing what you guys are doing with just pictures. It's tough. It is tough to do this at home. And you guys need to ask for more help, okay, if you need it at home. So, single chain versus double chain, augite, hornblende. And yeah, you can't really see it. The one bottom right here, you can kind of see it, not up close. I can see it on my screen, and maybe from back there you guys can see the layering is horizontal this way. All right, whereas this one, you might find a crystal length in there somewhere, but it's just way more granular. And as I said, augite also tends to be a bit blackish greenish, not just black. And those are important distinctions because, again, that's the point of the practical. You're going to have those in front of you, you're going to have to say, oh, crap, this is blackish green and grainy, and this one's black toothpicks. Okay, black toothpicks was hornblende. Because you want to get them right. You're not going to have those tables. You're not going to have your scratch kits and stuff like that. So you got to learn to recognize these guys. I don't know why they drew the line at 3. I think 4 looks a lot more like a sheet than 3, but if you get more than 3 chains side by side, they call it a sheet structure. So you have single chain, double chain, sheet. Anything come to mind that you saw the other day that might be a sheet silicate? Well, you had 2 for sure, all right? You might not have noticed in one of them, depending on how thick of a specimen you got. But your micas, you saw biotite and you saw muscovite yesterday. And those are like a deck of cards, okay? Except the sheets are glued together a little bit more. With the micas, it's kind of like the olivine. It holds together. You can throw it at someone and it wouldn't fall apart. But if you pick at it, it will start to flake apart rather easily. So we don't have those bonds between the layers. We're going to actually add that at the next level. But the crazy thing about those micas is that, as we just said, between the layers, there's not a whole lot going on there. But you could literally take one of those thin sheets and bend it between 2 fingers and practically touch it together without it breaking in half. All right? They're that strong of bonds going all the way across in the thousands probably of little molecules that are in one single sheet. So very, very strong structures that way. Okay. You also see talc. Eventually you'll see talc. Talc would look layered as well, but it's so soft from everybody rubbing it and saying, ooh, silky talc. The edges disappear over the years. And this is one instance also, for what it's worth, where cleavage lines up with the crystal structure. Okay, you have one of your cleavages is sheet cleavage, right? And it's mentioned like stacks of paper, deck of cards, whatever I used in the lab book. I forget the reference, but it's the exact same idea. And in this case, they line up right across here. You are seeing the cleavage when you're seeing these sheets. There's your muscovite. That's the light one. I guess I don't show you the dark one. The dark one's biotite. But you can see here, hopefully, you've got these broken layers there that are showing it, kind of indicating that there were sheets involved. Last but not least is something called framework. And I mentioned that those sheets, even though there's multiple present in, say, a mica, they're not bonded together top to bottom. Okay. At this point, you're using up all 3 of the corners of your little pyramid there. Every one of those oxygens is bonded to another oxygen next to it. That's how you get that nice wide flat sheet. You're not using the top one, though, the top of the pyramid. When we move up to framework, that's finally what we're doing. We're taking that top oxygen and we're bonding it to the bottom of the pyramid above it, if you follow. So now you're finally using all of your oxygens, and you're bonding this in all 3 dimensions then. Got a rather low-tech animation. Oh no, it's not even going to work. Because I'm not in display mode. But I have another a sheet that would go over that top one there to make it appear and disappear, but it's not working today. So these framework structures, these are your quartzes and your feldspars, and I'd like to think it's no coincidence that not only are those some of the strongest, hardest minerals that you'll find in your collection, but they also have then the strongest bonds, holding them together. You're using all of your oxygens in all of the directions, holding that structure together. Now, if you've been following and keeping up here, and you're saying, okay, so I see how we're moving from one, and then we're gluing them together, and then we're gluing a couple more together, and then we're gluing the tops and the bottoms together. I followed all that. But how that makes you move from a piece of rose quartz to mica to back to like something like olivine, I agree with you, okay? It isn't self-evident. And I indicated this a little earlier, all right? But it is a big hunk of the reason why. You just kind of got to trust me on that one. And that's why mineralogy can be discussed for an entire semester, because there's a lot more to it. But at any rate, at this point, we're going to leave it at that, all right, and just insinuate to you that this accounts for a lot of the differences that you see. It's also no coincidence that 75% of the crust is composed of framework silicates. So go back, and we told you that 25% of the crust, compositionally speaking, is silicon and oxygen, and that makes the silicate group. And the silicate group is the most commonly occurring group in the crust. Now we're saying that in that most commonly occurring group, 3/4 of the stuff you're going to see are these guys. And the reason I said that it's no coincidence, at least in my mind, is that if this is the most durable stuff, and we're looking at about 4.5 billion years worth of history here, it makes sense that over time you would concentrate towards the more durable, all the stuff that's flimsy and the micas in the world, okay, and the big hunks of olivine. That stuff would sort of break down and get included into other stuff, and you're not going to see it, necessarily represented like it originally was. But the more durable stuff is able to hang around. So that's my take on it at any rate. So when you see a rock, when we move on to talking about igneous rocks, you should not be surprised to see quartz and feldspar over and over and over and over again. You got a lovely picture of some quartzes there on the left, and 2 feldspars that we see in class. You got your orthoclase there on the left. Orthoclase goes by a couple different names. All right, we use orthoclase, and then albite on the right. Your albite was a little darker, a little grayer. Salud. But same stuff. And that, my friends, is what I have for you for mineralogy. Let me pause here for a minute.